I was just very, very lucky to be at the right place at the right time. I applied to NASA and was very fortunate to get a job. And I was working in the materials laboratory, the materials division. And I was able to use a lot of my prior experience because Dr. von Braun was a visionary. And in the Space Act of 1958 that created NASA, there was a paragraph that said that we would develop a nuclear-powered rocket stage to go to Mars. And that program had just started when I entered in with NASA. And so that was really the first project that I worked on. So I went from nuclear-powered airplanes to nuclear-powered rockets. However, it wasn't long before that program got canceled. I probably worked on more programs that got canceled than anybody's worked on in their lives. But it was my opportunity to really become quite familiar with the materials program and the material laboratory capabilities. And as a result of that, I became the chief of the projects office in the materials laboratory. And the materials laboratory's function was at least twofold. One, it was to anticipate all of the kind of materials that we would need in future projects and do the development work to have them available. And then more immediately, to work directly with the designers and the fabricators and the inspectors to solve the day-by-day problems that were coming up on the Saturn V. And we had other projects going on at the same time, so we were involved in all of those. But it boils down to the fact that in building a rocket or anything else, it's hard to do it out of anything other than materials. So we were involved in every single aspect of the program. And that was very challenging. Now, we did not have the palette of materials that we have today. Many things we had to develop from scratch, or we had to modify existing materials, or we had to requalify existing materials for the more severe environments that we would experience during the Apollo program. So that is how I got involved into being a rocket scientist. Now, your question was, how did I prepare to be an engineer? Well, actually, I was a scientist, but it didn't take much to learn how to walk and talk like an engineer. So most of what I did, of course, was engineering, and that turned out to be a very fruitful profession. Every day, we were confronted with issues that nobody had ever thought about, simply because there was far more that we did not know about going to the moon than what we did know. And every time we solved one problem, it seems like it created 3 more problems that we hadn't thought about. And that was just your daily life, just step by step by step, figuring out how to get to the moon and back. So through that process, I guess I became an engineer. And then after the Apollo program, basically went into engineering management. The Saturn V particularly was probably the worst possible combination of every severe environment that you could think of. And therefore you had to come up with materials that were going to survive under all these conditions. For example, you had 7,000 degree gas coming out the exhaust. You had liquid hydrogen coming in at minus 423 degrees, so you had a 750 degree temperature differential. The engines were shaking and tearing themselves apart. We had the turbo pump rotating at 36,000 revolutions per minute, creating a tremendous environment. We had materials that had to be dissimilar, so we had to introduce things like galvanic corrosion. I mean, we were operating out of Cape Kennedy, which is the worst corrosive environment that you can find. So everything that you think about in going to the moon caused very severe decisions to be made about the materials. You're starting out in an environment, for example, launching from the Cape, it's hot and humid. Then you go into a vacuum environment. On the way to the moon, if you happen to be in the sunlight, it's 250 degrees Fahrenheit on one side and minus 250 on the other side. So we actually, on the way to the moon, what we call barbecued the spacecraft. We rolled it in order to equalize the temperature as we were going there. But you had to think of all of these kinds of things and say, every nasty environment that you can think of, you were confronted with in that kind of program. Of course, the main thing was we had to find materials that were very strong, had a very high mechanical properties, at the same time were light, because we had to keep this vehicle as light as possible. And that drove us to do a lot of things in terms of how we designed the structure, also in terms of how we compounded the materials, and we able to say we had to invent some new materials to accommodate these kinds of things. So it was a very significant challenge to get to the moon and back. And as a matter of fact, that's probably one of the most important things for the public to come to appreciate. Putting people on the moon was a political victory, and that's clear. But the value of the program is all the technology that we had to develop to do it. Because we are living today off the technology that was started in the 1960s.
That's true.
Now, the pertinence of that is the only thing that this country really has to sell on the world market is technology. We don't have raw materials that we can sell. Our labor rates are certainly not competitive. People don't buy our products because of quality. They want our technology. And yet there is no program in this country driving technology. And the third world countries either are or are beginning to catch up with us. And that's probably the greatest justification in the world to tackle something as complicated as going to Mars. Just the technology to get us to Mars and back will fuel our economy for another 75 to 100 years. And that's why that is so important. It does not have to be a trip to Mars, but there are few things more complicated and more demanding than a manned flight to another planet. The way I look at it is, by not doing this, we are cheating my great-grandchildren. They will not have the advances in technology relative today that we experienced when we grew up from being children. Saturn I and Saturn IB were the workhorses in the program because they had the largest lift capability of anything in the world. We needed that capability to put the command module and the service module for the Apollo program in orbit to develop it. So the Saturn I and Saturn IB were kludged from existing hardware. We took a Jupiter tank for the center, 8 Redstone tanks and clustered them around the outside. Then we used 8 Titan engines, which were the largest engines in the world, and upgraded them. And that gave us just 1.5 million pounds of thrust, which was just barely enough to put the command module and service module into orbit. So it was also the workhorse for putting the astronauts in orbit early in the program, so that because that's the heaviest lift vehicles we had. Now, the difference between the Saturn I and the Saturn IB was not so much in the booster, but in the second stage. We built the first of all, the liquid hydrogen and liquid oxygen is the highest performance fuel for a rocket engine. Nobody had ever built a liquid hydrogen, liquid oxygen engine, but we built the first one called the RL-10. The RL-10 was a very small engine. So we used 6 of those small RL-10 engines on a stage that we called the S4 stage. And that gave us an opportunity to lift heavier payloads into orbit. And it was also an interim to learn how to use liquid hydrogen and liquid oxygen and to develop the launch vehicles to accommodate them while we were developing a more powerful engine called the J2. Now, when the J2 engine became available, then we put it on a stage and it called it the S4B. So the S4 was really a learning opportunity to prepare us for using the S4B. And as a matter of fact, we launched 10 Saturn Is and 10 Saturn IBs through the life of the program. So that was a very important step in our learning. Now, the beauty of this was that the S4B was also and going to end up as the third stage of the Saturn V. So we were developing it, proving it, as we were developing the first two stages. Well, in the first place, the technology of the Saturn I had very little benefit to the Saturn V. The Saturn V was starting from scratch. In fact, almost all of the design of the Saturn V was done from first principles. None of the prior work really benefited us a great deal as far as the requirements for the Saturn V. The Saturn V was just so huge that it required a whole new philosophy. It required whole new materials. We had to go to manufacturers to actually get them to produce materials that we could use in order to build the Saturn V. So Saturn V was basically starting with a clean sheet of paper. Fortunately, of course, we did use the S4B stage. That gave us a heads up there. But the S1 first stage and the S2 stage, second stage, were done from scratch. Now, we used an entirely different group of materials. For the Saturn I, which was a derivative of small ballistic missiles, the Redstone and the Pershings, they used an aluminum alloy called 5456, which was good, but we then switched to aluminum materials that were much stronger, much better, more easily weldable, and so on. So basically, the Saturn V is made out of aluminum. But we used all flavors of aluminum, different alloys of aluminum. Every single material that went into the Saturn V was selected for that specific application to maximize its properties and performance and minimize weight. So there were places like on the S1C stage, the first stage, where we used an aluminum alloy. It was an aluminum copper alloy that was easily weldable, had good strength. For the upper stages, where we were going to use liquid hydrogen, we used a different kind of aluminum, which was called 2014, which had the highest mechanical properties at liquid hydrogen temperature. In other places where we didn't have tankies and we were just trying to hold the whole structure together, we needed the strongest materials that we could find. We used yet another kind of aluminum alloy called 7075 that was very, very strong, but you couldn't weld it. So we had to come up with other kind of manufacturing techniques to use that alloy. So every single material that went into the vehicle was designed and tested for that particular application. We went from a sheet of paper to a first flight in 7 years, which is phenomenal. But we had to develop a lot of new materials. And when I'm talking about materials, the first thing that comes to mind, of course, are metals. That's the first thing people think of. But we have a lot of organic materials. For example, the heat shields that we had to build to protect the fuel tanks from the radiant heat from the exhaust were basically rubber-like materials. So they had to take the heat, they had to be flexible and very strong. You think in terms of lubricants of oil or WD-40, well, you can't use those in space because they evaporate. So we had to invent solid film lubricants, basically graphite, which is used in virtually all products we have today. And that's really the beauty of this, that these materials that were developed for the space program ultimately ended back up in the commercial market. And they are used in products that people are use commonly today and have no idea where these things came from. But this gets in also to the electronics. All of that gear is made out of materials, and those are very different kind of materials than metals. So you're dealing with everything you can think of. We had to insulate the liquid hydrogen tanks because the temperature of the liquid hydrogen had to be kept at minus 420 degrees Fahrenheit. That involved foams and spray-on foams and foam materials. So virtually every kind of material that you can think of, we encountered at one place or another. And one of the things that we characterized all of the programs that were worked on by the Marshall Space Flight Center is we tested and tested and retested. We tested every component to failure. So we knew how much margin we had in the design. That was really the downfall of the Russians in the competition with us. They had a huge rocket with 40 engines on it. They never had the capability to fire them as a cluster on the ground. And every time they launched, something went wrong and it blew up. So we were fortunate to have a culture that was conservative and very much test-oriented to make sure that we knew exactly what was going to happen. Now, later, when the young engineers came along and started working on the SLS, they tried to reverse engineer what we did, and they said, this vehicle is over-designed. Well, we knew it was over-designed, done intentionally.
Right.
The first part was to make it conservative. The second thing was it was designed to go to Mars, not the moon. So we were very, very confident in the vehicle. And every day in the design work or in the activities that were going on, every decision that you made was a life or death decision. And you were very, very conscious of that. No decision was done lightly. You thought about these at night and you worried about them. And every decision involved virtually everybody involved in the program. And I think that's one of the real characteristics that in those days, you had to be able to communicate very effectively with everybody. When we had a problem, you got on the telephone, you called up everybody that you thought was involved, and you got together and you sat down, you argued about how to solve the problem. You came up with 2 or 3 approaches and then said this is the one that's best. Then you went and told your boss, this was the problem, here's the consequences of it, here's what our solution is, and here's what's going to happen if you don't do it. And so it was a very effective management system. And I think people overlook the fact that one of the real significant products of the shuttle or the Shuttle Apollo program was the management system. At the height of the program, they're down to the lowest suppliers. There were 450,000 people working on that program. You had contractors in half a dozen different areas building major parts of the program. When we designed the Saturn V, for example, the first thing that we realized, or we knew, there was no tooling anywhere in the world large enough to build the parts. So we had to design and build all the tooling, and then the factories to put them in. When you build a component, you had to move them from place to place, so you built the transporters. When the stages were completed, they had to be shipped to the Cape. We had to design the transporters to get them there. Those that are built here or in Mississippi, we had river-going barges. The S2 stage was built in California, so we built an ocean-going barge that went through the Panama Canal. The S4B that we talked about earlier, we took an old C-99 airplane and cut the nose off and put a big bulbous container on it. And that container really gave it its name because when you sat and looked at the airplane, it looked like a pregnant guppy, and that's what it was called. And you could slide things right in there and fly them to the Cape. So what I'm saying, and they built all the test hardware and so on. So what I'm saying is there were half a dozen major programs all going on in parallel. And the management team and scheme that we came up with to integrate and control all of that in itself, I think was one of the major products of the Apollo program. One of the things that really bothers me today is we are losing communication skills. When I'm touring children through the Saturn V hall, I always take an opportunity to point up to the Saturn V and say, you cannot do that by Twitter or email. Yep. You've got to be able to communicate face to face and work things out. And that's a skill that we must make people really appreciate if we're going to have a viable workforce in the future. Leading up to the first flight, of course, there was years and years of testing that had gone in on every part that we could possibly think of. Plus the fact that we built the vehicle conservatively by putting in redundant systems often. Quite often we had triple redundancy, so if it failed the first time, nothing happened. Failed the second time, nothing happened. Failed the third time, it failed safe. So we went overboard in trying to make it 100% reliable, if that were ever possible, and it turned out to be. But leading up to that point, of course, we went back and we reviewed everything we'd ever done, every decision, all the analyses. And before every flight, and of course, particularly before that first flight, we had what we call a flight readiness review, where we got all the experts together and all the managers together, and then we went through every part of that vehicle and saying, here's all the things that have been done, here's how we did, so on and so forth, and yes, we believe the thing is ready to fly. It so happened that I was part of that discussion, and I gave my presentation on a lot of the constraints for a successful launch. These are the criteria we had to meet on launch day. And when I finished, Dr. von Braun said, I'd like for you to pack your bag, you're going with me to the Cape. So I was drafted into the launch crew for the very first flight. And that has got to stand out as probably one of the most significant and rememberable parts of my career, simply because it was the first time. We had poured our hearts out for 7 years building this thing, and there it sat 3 miles away. When you pushed the button, it was either going to go or it wasn't. And that was on November 9th, 1967. I'll never forget that date, 7 o'clock in the morning. That was a very emotional moment. When it lifted off, liquid rockets, and particularly one that huge, moved very, very slowly. It looked like it was never going to clear the launch tower. And of course, as you burned up fuel, it picked up speed and went. But I'll tell you, I don't think that there was a dry eye in that control room. It was like sending your child off to school for the first time. And that was our baby. And here it was, it was going to go. But it was a beautiful launch, and of course then we followed that with 12 other very successful launches. But that was a very significant moment in my career. Every day was important, every day was exciting, but that was a first, and I will always remember that one. When Congress cut off the money for the Apollo program, we still had 3 missions planned that we were going to fly. This was a time of dire concern for NASA because all of a sudden our mission disappeared. And we were in a mode of trying to decide where we could go next and what we could sell the Congress on and the public as the next step into space. So Dr. von Braun created the Program Development Organization, which was really a marketing group or an advanced design group. Dr. Bill Lucas was the director of that group. And it was our job to think outside the box, come up with every idea that we could think of, and the techniques and the paths to develop space into the future. When Dr. Lucas became the director of that, he was my former boss, and so he asked me to join him. So that's how I got into that. In program development, we actually came up with a number of ideas that ultimately took fruit. For example, the Space Shuttle came out of that program. Hubble, Chandra observatories, the high energy astronomical observatories came out of that. So there were many programs that we eventually got funded that were the result of this advanced design effort, which is really what it was. And we were trying to define our future is what it really boiled down to, and the future of the nation's space program. And fortunately, there were some very good products that came out of that. All right, first of all, you wanted a very reliable capability to get man and materials to low Earth orbit. and you wanted this to be done economically. Also, you needed to have the capability to launch large payloads and large crews of people, because we wanted to take advantage of the scientific opportunities in low Earth orbit. So those were very strong drivers. Now, those drivers resulted in the fact that we began to focus on a reusable vehicle. In the very first designs, we had a totally reusable vehicle. We had the orbiter, which is a rocket-propelled space plane, mounted on top of another very, very large rocket airplane. The idea being that we would launch that combination to a very high altitude, then the orbiter would fire and take it into orbit, while the bottom part would fly back to Earth, be refurbished, and we'd fly it like a normal commercial airplane. The problems of developing two brand new major rocket airplanes at the same time was both expensive and challenging from a schedule standpoint. So we had to ultimately look for other ways of getting the orbiter into orbit. And that's what led us to the basic design that people are familiar with. That in order to make the orbiter as light as possible, we decided we were going to put the fuel in a separate tank, the external tank. And the orbiter was mounted on top of the external tank. The external tank then became the backbone of the whole structure, because then we had the two solid rocket boosters that were mounted to the external tank. Now, that, of course, put a lot of stress on that external tank, and we had to do a lot of materials work in order to accommodate the loads from the solid rocket boosters and the weight of the shuttle orbiter sitting on top of it. And of course, with the temperatures of the fuels in there ranged from minus 273 degrees to minus 423 degrees. So that was a very difficult job. But as a result of that, the shuttle program became very, very effective. Of course, we had 135 launches, and we learned a great deal about how to fly into space economically. However, I have to say at this point, in order to sell this program, we postulated and proposed flying a shuttle every 6 days. Now, that was not only unachievable, it was unrealistic.
Right. Every 6 days, that made me go, whoa, a marathon that.
There is no way that you could turn vehicles around that quickly. But at any rate, that was done in order to make a hypothetical cost per pound into orbit as low as possible.
Okay.
So we fudged a little bit on that.
It's a little bit of NASA math there.
That's right. But also, we partnered with the Air Force, and that also was helpful in our selling the shuttle program. And as a result of that, they imposed a number of requirements on the design of the shuttle. Unfortunately, those capabilities were never utilized, and they penalized the performance of the shuttle. So we actually gave up capability in order to accommodate these additional requirements. But nevertheless, the space shuttle turned out to be a very, very effective program. And even though we had 2 accidents, it is still one of the most reliable aircraft that has ever been built. So that was a major step forward in our getting access to space in a routine, convenient, and economical way. The Pathfinder started out as a tool. We were going to have to move the orbiter from the factory to various places to test stands and to ultimately get it to the Cape and so on. And we were going to have to transport this on roads and through various places. Pathfinder was designed to the same dimensions, although it was a very crude structural member. but it was the same dimensions. We hauled out all over the country, every place we were going to have to take an orbiter to make sure that there weren't any power poles in the way, or the trees were not in the way, or that you could get it through underpasses and so on, to that, things of that nature. And so that was a very valuable of the program, but it was never never fancy like a flight orbiter. I mean, it was purely a tool. Its second life came as a result of the Japanese. They wanted an orbiter. Of course, all of our flight orbiters were being used, so that wasn't going to happen. So Pathfinder was reconfigured. We put a fuselage and a shell around it and made it look like an orbiter. And that served that purpose for a while. And then its third and final life happened when it was brought back here. And it's part of our Space Shuttle display. And I would have to say that contrary to most people's thinking, we have the only Space Shuttle mock-up in the world. Now there's a nomenclature problem. A lot of people refer to the orbiter as the shuttle. It is not the shuttle, that is the orbiter. The shuttle is the orbiter plus the external tank plus the 2 solid rocket boosters. It is the entire package. And we happen to have the only one in the world right here at the Space and Rocket Center. We had to develop a lot of new techniques, a lot of new materials, and a lot of new processes. We were constantly required to take out weight. Every time we turned around, somebody wanted to take out, largely because the spacecraft weight kept going up, up, up. First thing we did, we had the initial external tanks painted white in order to protect the foam underneath from ultraviolet radiation. Well, in the meantime, we had samples of the insulation being exposed to sunlight, and we found that we didn't really need to put the paint on there. So we then decided, well, we're going to quit painting the tank, and that saved 600 pounds, 900 pounds. Also, there were demands for more and more weight reductions. So instead of building the tank out of the 2219 that we used on the Saturn V, we went out and developed a whole new alloy. That's an aluminum lithium alloy that had the strength of aluminum but was much, much lighter. And that was what we called the super light tank. Constantly you're working on these things, trying to improve the spray foam insulation on there was always a challenge. We ran into a problem one time when we started to spray the tanks and the material just wasn't working right. And we're doing the same thing we always did, but it just wasn't working right. So we did a chemical analysis, and we found out that the manufacturer, the supplier, had changed the chemistry of the products that made the foam. So we had to go to this manufacturer up in Buffalo, New York, and to found out that, well, they were selling the same material to the commercial market. And in order to save money and make more profit, they changed the chemistry and didn't bother to tell anybody.
Wow.
Well, in that case, we negotiated with them, and we got them to make enough material of the proper chemical composition that we could finish building the shuttles that were still remaining. So we had to work around those kind of problems. And when you're dealing with commercial problems, that's always an issue. Every batch of material that we got shipped in, we had to test it to make sure that it met specifications. Because you never knew when somebody was going to make some little change. And when people talk about, $500 hammers and things like that, criticizing the space program, it's not the hammer. It's all the documentation and proof that it's a right hammer that cost you. And the same thing, every material that came in, we tested it for its chemistry, we ran mechanical properties to make sure that we had exactly the material we needed. And so that whole philosophy then continued on into other programs. In welding, we developed friction stirred welding, which was much more efficient in that it created fewer defects, and we could have much purer welds in the vehicle. So that was a very significant cost savings. And you can go on and on and on. Now, where did the legacy of Space Shuttle lead us to today? Well, the current program being built, the Space Launch System, or SLS, is basically a shuttle. The core section of that is nothing but the external tank of the shell elongated. The solid rocket boosters are identical to the ones we used on shuttle, except we added one more segment. And so it is simply a clone, if you will, of the space shuttle. So we took advantage of all of that experience and all that technology in building the new vehicle. And that, of course, saved us a great deal of money, not having to develop new materials and new processes for the space launch system. I was a project manager on the space shuttle. I was deputy project manager on the external tank. I was project manager on the advanced solid rocket boosters. I was project manager on the space shuttle main engine upgrade, and project manager on the shuttle systems and integration. So I had a great involvement there. Then we decided that we wanted to have an opportunity for on-orbit manned laboratory capability. And I headed up a program called the Research and Applications Modules, which was basically the size of a school bus that fit inside the cargo bay and was an on-orbit laboratory. About this time, the European Space Agency decided they wanted to get into our space business, into our space program. And so I and 2 or 3 other people went over and met with the ministers, representatives from each of the countries involved, and discussed the project that we had in mind for the Spacelab, and whether they could take that job on. The ministers were very reluctant. They were concerned that they did not have the manufacturing capability there. Of course, they, at that time, had never built any rockets or anything, and that they were concerned that they might ultimately end up with a black eye for the European community. One of the things that we did was visit their manufacturing capabilities, and we had talked to them, convinced them that yes, they had the capability to do this. So they did agree, and they built the Spacelab to fit inside the orbiter. Well, as a result of that, I was asked to come over and be an advisor to the European Space Agency. So I spent between 2.5 to 3 years over there working with all of the companies, trying to ease their concerns and help them solve problems. And I was out inspecting the hardware every day. When I found something that, I'd either give them some suggestions, or I would call back here and get our experts to come over and work with the Europeans to solve those problems. So it was really a very interesting project and opportunity. If you think we have problems coordinating things, try to get 19 different countries to work together and communicate together.
Different languages.
And all different languages, different cultures.
Different cultures.
But they did a great job on that. So that's how I got to be into that job. But it also opened up a lot of other opportunities. Since they didn't know what to do with somebody like us, I was assigned to the U.S. consulate in Bremen. So I got to participate in all the consulate functions. They invited us. And every time that there was a dignitary from the United States coming over, I had to be there to greet them and so on and so forth. But it was a different environment.
A different environment, a fun kind of side apart to what you had been doing with NASA, yet still involved with it. So it's very interesting.
But it was a successful program. Very great. In order to take advantage of the full capability of the shuttle, we wanted to give scientists an opportunity to work in zero gravity and have a laboratory large enough that they could do meaningful things. So as I said, we developed the Spacelab. The Spacelab was really a miniature space station. The modules that we use to build the International Space Station today evolved from Spacelab. It was just one that you could assemble together and make a bigger thing. So it really was our precursor to the International Space Station. And it was very, very successful. So making it, it was just a matter of designing a habitable fuel tank is really what it boiled down to. We were accustomed to building fuel tanks. Now we had to design one that was habitable. That, of course, introduced a lot of new problems and a lot of different things. But the simplest way to explain Skylab is simply say it's one module from the International Space Station located in the cargo bay of the orbiter. We originally had a total U.S. station called Space Station Freedom. And then the country decided they wanted to bring in other countries, basically to share cost and share expertise. And so there was a very small team that was put together to try to make a conversion between Space Station Freedom and the International Space Station. And I was a part of that activity. And we, in fact, did come up with the concept of how to convert what was already being done into the International Space Station and evolve the configuration and the design that is flying today. Since I lead tours out here at the Space and Rocket Center, we quite commonly get people who come in and say, is there still a NASA? Are we still doing anything? It's surprising how many people do not realize that anyone under the age of, 18 or 20, has lived in a period of time when there have been people living in space continuously through that period of time. And yet there are people who don't even realize there's a space station up there. One problem that we have is that people have no concept of what we're doing and how it's benefiting them. We have never told the public, or we never told the public, what we were learning about going to the moon. We never published that. We never made a big deal of it. Same thing is true on shuttle. We never published, they were published in technical journals, but the public doesn't read those. We never really educated the public of what has come out of these programs. The same thing is true on Space Station. There are 2,000 experiments going on Space Station, half of which are designed to make life better here on Earth, not in space. And yet the public doesn't realize it, and it's not their fault. It's we've not really done the job that we could do in educating them. And that is so important because I think, as we said much earlier, that all the things the Apollo program certainly was a political program, political project. But all of the technology that we have today has come out of the space program. And there is no program in this country driving technology. Well, I'm often asked that question, but in a little different sense. Quite often we get the question, what was the most important thing you did? Frankly, we never thought in those terms. Very few people thought that way. It was always, what did we do? I think that the Apollo program was probably the greatest peacetime team effort in the history of mankind. Everything we did had to be the result of very intimate team activity and team effort. We never really thought in terms of, what did I do? I contributed to a lot of things, but I could not have done anything without the involvement of hundreds of other people being involved. And I think that's a very important legacy, particularly today. I think it is so important that we develop team concepts. That our society seems to be going the opposite direction in many ways. But the legacy, I think, is for the young people coming along. It doesn't make any difference how difficult it is. When we started the Apollo program, 96% of the people that we talked to said it's impossible. You cannot do it. You're going to strand people on the moon. You're going to lose them on the way to get there. It just, you're just pushing the envelope too far. You cannot do it. But the message is that if you put your minds together and you work as a team, you can accomplish almost anything.